Good day everyone, my name is Prince Maxi S. Morastil and my topic for today is linear programming simplex minimization method. So, for introduction, the simplex method is an approach to solving linear programming models by hand using slack variables, tableau, and pivot variables as a means to finding the optimal solution of an optimization problem. A linear program is a method of achieving the best outcome given a maximum or minimum equation with linear constraints. Most linear programs can be solved using an online solver such as MATLAB, but the simplex method is a technique for solving linear programs by hand. To solve a linear programming model using the simplex method, the following steps are necessary. So the first step is standard form, introducing slack variables, creating tableau, pivot variables, creating a new tableau, checking for optimality. So next, introduction for minimization method. This document breaks down the simplex method into the above steps and follows this example linear programming model shown below throughout the entire document to find the optimal solution. So minimize. This is the solution, or this is how you do it. Negative z equals negative 8x sub 1 minus 10x sub 2 minus 7x sub 3. Then st equals x sub 1 plus 3x sub 2 plus 2x sub 3 is less than 10. Then negative x sub 1 minus 5x sub 2 minus x sub 3 is greater than negative 8. So x sub 1 and x sub 2 and x sub 3 is greater than 0. To the next slide. Simplex minimization method. We applied the simplex method only to linear programming problems in standard form where the objective function was to be maximized. In this section, we extend this procedure to linear programming problems in which the objective function is to be minimized. So, a minimization problem is a standard form if the objective function is w equals c sub 1 and x sub 1 plus c sub 2 and x sub 2 plus and so on is to be minimized subject to the constraints. So a sub 11 and x sub 1 plus a sub 12 and x sub 2. And this is how you solve it. And then where x is greater than 0 and b is greater than 0. The basic procedure used to solve such a problem is to convert it to a maximization problem in standard form, and then apply the simplex method as discussed here. And then we use geometric methods to solve the following problems. So this is the problem number 1 for minimization method. And this is how you solve a minimization problem. First, you find the minimum value of w equals 3x sub 1 plus 2x sub 2. Then subject to the constraints, then this is how you do it. 2x sub 1 plus 2x sub 2 is greater than 6. Then x sub 1 plus x sub 2 is greater than 4, where x is greater than 0 and x sub 2 is greater than 0. So the solution, the augmented matrix corresponding to this minimization problem is, so as you can see in this table below, this is how you solve the problem here for minimization. So 2, when you do that in the table, thus the matrix corresponding to the dual maximization problem is given by the following transpose. So then you transpose this in this table, then this implies that the dual maximization problem is as allows dual. Then you do the subject to the constraints where 2y sub 1 plus 2, I mean y sub 2 is less than 3, then y sub 1 plus y sub 2 is less than 2, where y is greater than 0 and y sub 2 is greater than 0. We now apply the simplex method to the dual problem as follows. The next, and this is how you do it. So this is the basic variables, the y sub 1, then departing, so then entering at the table, then as shown here at the table, this is the basic variables. Then from this final simplest tabli, we see that the maximum value of equals is 10. Therefore, the solution of the original minimization problem is w is equals to 10. So the answer is the 10, and this occurs when x sub 1 equals 2 and x sub 2 is equals to 2. Both the minimization and the maximization linear programming problem is in example 1. So it could have been solved with a graphical method as indicated in the figure. Then the maximum value of equals 6y sub 1 minus 4y sub 2 is the same as the minimum value of w is equals to 3x sub 1 plus 2x sub 2 as shown in the figure or in the table. Next, example number 2 is just the same as example number 1. Is find the minimum value of w is equal to 2x sub 1 plus 10x sub 2 plus 8x sub 3. So this is the objective function subject to the constraints. So the constraints is x sub 1 plus x sub 2 plus x sub 3 is greater than 6. Then x sub 2 plus 2x sub 3 is greater than 8. Then so on and so far. Where x sub 1 is greater than 0, then x sub 2 is greater than 0, then it's the same as x sub 3 is greater than 0. So next, so the solution is just the same. You make a table, then the augmented matrix corresponding to this minimization problem is this table shown below. Thus, the matrix corresponding to the dual maximization problem is given by the following transpose, as you see in this table. Then this implies that the dual maximization problem is as dual maximum value of equals 6y plus 1 plus 8y sub squared plus 4y plus 8y sub squared plus 4y sub 3. So this is the dual function subject to the constraint. So this is the dual constraint is y sub 1 minus y sub 3 is less than 2, then so on and so far. So where y sub 1 is greater than 0, and then so on, then y sub 3 is greater than 0. So we now apply the simplex method to the dual problem as follows. So as you see here in the graph, this is how you do it. So next, and this is how the basic variables, then you do the departing and entering the numbers just as shown at the table. So this is how you do it. So next, for this is for the question number 2. Then next is, from this final simplex tableau, we see that the maximum value of z is 36. Therefore, the solution of the original minimization problem is w is equal to 36. So the answer from the question number 2 is 36, and this occurs when x sub 1 is equal to 2, then x sub 2 is equal to 0, and x sub 3 is equals to 4. So the final question or the final problem is this one. So a small company owns 2 refinites, then you'd see here the solution, and then where the constraints is just the same as question 1 and question 2. So you do the same. Then where x sub 1 is greater than 0, then x sub 2 is greater than 0. Then you do the augmented matrix, same as 1 and 2. And this is how they show at the table. So as you can see at the table, the matrix corresponding to the dual maximization problem, then apply the simplex method, the dual problem as follows. Then you do that as the table shown below. Then from the third simplex tableau, we see that the solution to the original minimization problem is this one. So C equals to $1,750,000, and this occurs when x sub 1 equals to 25, then so on and so far. So this is the solution. So that's how you solve a tree minimization problems from simplex method and from linear programming. That's all. Thank you.